Hello, I'm Clare Macrae and welcome to my talk where I give you some tips and tricks to quickly and effectively test Qt desktop applications. My main audience for this is going to be developers who are working with Qt code. There are some slides throughout here that will be useful about testing in general and testing GUIs in general, but the main focus is Qt. If you'd like to know more about the approval tests, mechanism and library for testing, then the link at the bottom of the screen will point you to previous talks that I've given, but this is the first recording of a new talk. So a little bit about me. I've been programming in C++ and Qt for more than 20 years now, but my real focus, my real passion is learning and sharing information about testing legacy code, making it easy and effective to work with code that many people think is too hard to test. And I'm the co-author of the approval tests for C++ library, along with Llewellyn Falco. Last summer, I set up a consulting company to help me go further in sharing this knowledge. Contact details are on the last slide as well. There are many links and references in this talk, and you can get to those online via the bit.ly link or the QR code. And again, that's at the end if you want to grab that. A little bit now about this talk. The first thing to say is Cambridge is getting fibre broadband. The bad news is my street is being done this week and there's a couple of building sites nearby. So at the moment it's quiet, but if there's any odd rumbling going on, I apologise, it's out of my control. Throughout the talk, occasionally a slide like this will pop up, any questions, and I will then have a look at the questions that people have been asking in the Q&A section on Remo. I'll try and focus on questions that are relevant to the section that I've just talked about. If I don't manage to answer all the questions today, or if you want to talk more, I'll hang around in the fuzzy track in Remo afterwards. And I hope to say hello to you then. So here's the scenario that we're working with. You have inherited some legacy Qt code and it's valuable. You need to make some changes, but it doesn't have tests and it wasn't designed for testing. So you get into this vicious circle that you can't add tests because you can't safely refactor. And the majority of this talk is helping you break that side of the circle, but specifically for Qt desktop applications. You don't have any tests and the code wasn't designed for testing. I'm sure many of you know that Qt, or Qt, as it is also called, is a massive framework for cross-platform framework for writing rich and beautiful graphical user interface applications on many different platforms. I firmly believe that Qt's GUI powers make automated testing harder than testing non-GUI code. There's so much more to deal with in the way of interactions and platform differences and things like that. But my goal for this talk is to give you the confidence to start testing your own Qt application and doing so effectively. And to that end, how do you even start adding tests to an existing application? Well, the answer is that you don't modify the main of your existing application. So here's the strategy to adopt. So imagine you have got your executable, your program that you're testing, be it a GUI one or otherwise, and that has a main, and it has the headers and the CPP files. And if it's a Qt GUI application created with Qt Designer, it'll have a bunch of UI files as well. And what you need to do is change your build system to divide that into two, so that your GUI program links the main and links in a static library, which here I've called UI.lib, which contains all of the other CPP files and the UI files as well. And once you've created that static library, you can then write a new test executable, which I've called UI Tests for lack of imagination, and it will contain its own main and its own test CPP files. So the UI code, the majority of the code, the implementation is compiled once into a static library, and then two or more executables link that library. If it's too hard to move everything in one go, you could always just move incrementally the code that you're writing tests for. And the first rule of adding tests to legacy code is only look at adding tests for the code that you need to change. Don't set out to test everything in one go. You'll never get anything released if you do that. I'm sometimes asked, why does it have to be a static library? Well, if it's a dynamic library on Windows, you'll get lots of linker errors, and then you have to add lines like declspec, DLL import, and so on. That's faff. If you haven't done it before, it's tedious. Whereas if it's a static library, you don't have to change your source code on any platform. You can just change your build system. And then if it's an application that you release, if you use dynamic libraries, you'll have to change your release and distribution system to include those dynamic libraries alongside your executable. Whereas if you set up a static library, the code still gets pulled into the executable and you don't need to change your release process. So basically, static libraries are a smaller change. I'm not saying don't use dynamic libraries. I'm saying if you're starting from no libraries at all, static libraries are the smallest incremental step. And if you want to know more about that and you're using CMake, then Arnie Metz, back in 2018, wrote a lovely set of 4 posts explaining that transition. So I recommend that to you. I'll pause at this point and see if there are any questions, and there aren't, so I will move on. A bit more context. Throughout this talk, I'm talking about automated testing being done by developers. So developers are writing code to test other code. So you might think of it as glass box or transparent box testing. So developers have access to the code and they can potentially change the code to make it easier to test. And then, of course, add new features and add tests for the new features. So how do you create your test executable? You need to have a runner, use a test framework that allows you to express the tests that you're writing and provides the code to drive those tests. And there are many to choose from in C++. Here are 4 reasonably well-known ones: Google, Catch2, DocTest, and Qt itself has its own test library. For this talk, it's mainly going to be Catch2 code with a little bit of Qt test code. But a lot of what I'm talking about applies regardless of the test framework that you're using. So don't worry, if you're not using Catch, there will still be plenty to take advantage of in the talk. So let's start by writing a main so that Catch2 can drive our testing of Qt code. We need to use hash-define catch config runner. You may be used to catch config main. This is different because we're providing our own main function. We need to tell catch that we're going to do that. So we define catch config runner, and then of course we include the catch header. Now we also need to have a Qt application object. If you don't know, the reason for this is if you try and create Qt widgets and there isn't a Qt application object in existence, the code will just crash, it won't run, you'll get errors. And so rather than making each individual test case create its own application, we create an application once in the main, and we pass in the command line arguments to it. So we can pass in things like -platform off screen. So we can, Qt has lots of standard supported command line arguments and we can use those. And then we create the catch session and we tell it to run. And again, we pass in the command line arguments that our program has given. So we can use, for example, --break to stop in the debugger if we get a test suite failure. And then the session runs and we return the result. So it's a bunch of slightly hard-won boilerplate code, but it works. And from that point, we can write catch tests and call Qt code. And so in order to have some examples, I reached out online and the wonderfully kind and friendly SuperCollider community got back in touch with me. SuperCollider is a platform for programmatically synthesizing sounds and composing music with algorithms. It's a lovely program. It's part of how Sonic Pi on the Raspberry Pi is implemented, if you've seen that. And it has its own integrated development environment, IDE, and that's what it looks like. So I'm going to start testing a tiny, tiny component of the Super Collider code. That's this little red square. So we always want to start with something small to start testing. And that's called a color widget. It's a color picker in the Super Collider source code. And the user clicks on a little square like that. A color dialog pops up. The user chooses a new color and then clicks OK. And then eventually the red square will change to green to indicate the new color. Very quickly, that change will happen. So that's what we're going to test, that little square. It's really important to say that you want to be focusing on testing the code that you control, that you maintain. So on the left is widgets in the application, like the application we're testing. On the right is Qt code and perhaps the odd dialog provided by the operating system. It would be a waste of our time to test that, and we wouldn't be able to fix any problems that we found. So we're going to focus on testing the code on the left. So here's our first test. So we have a catch2 test case. We give it a name. We create a color widget object. And what I'm doing in this test is just exploring, can I create an object? Can I see what its default state is? And it turns out that its default state is black and opaque. So that 255 means opaque. And so you see at the top corner, this black square indicating that I'm testing a black widget at the moment. So throughout these slides, I try and give some kind of reminder, some kind of position of where I am with pictures at the top right-hand corner. And then we use catches check to check that the color of the widget is the black expected color that we expected. Now, at this point, I have to confess that it took me a while to get that test to pass because I first wrote expected color is 0000, which turns out to be opaque. And you might know that Catch writes out really helpful information when a test fails, but it didn't know how to write out a Q color. So it wrote out question mark is not equal to question mark. It took me a while to work out that it was the opacity that was wrong. So then I wrote a little bit of code to teach Catch how to write a string representation of a Q color object. So Catch string maker, it's well documented. You can add versions of it for your particular types of object in your test. And then I wrote check that the color is, and that's more expressive than the magic numbers in the previous test. And in fact, when I first wrote that, I wrote a test which I knew was going to fail, check that the string representation of the color is an empty string. And Llewellyn Falco and Emily Bache call this approval testing. The idea that you start, when you're exploring functionality and trying to work out what's going on, get familiar with the code base, you write a test, sort of poke the code, write a test, see what answer you get, and then if you like it, you paste it into the source code. So now let's look at actually changing the state of the widget. So I am now going to simulate the user clicking and changing the color to red. But I'm going to do it by calling the setColor method rather than going through the dialog, color dialog. And that's because I'm wanting to write localized code. And I've looked at the interface of color widget and it has a setColor method. So it's reasonable to expect that that's how the user's request for a different color would be implemented. So I've done the arrange, I've set up the widgets, and now I'm acting, and then I'm going to assert that the color has changed to red. It's a tiny, tiny test, but it's part of getting to know the library and exploring it, and where tests are useful, saving them along the way. Now, you would be forgiven for thinking quickly testing. That hasn't been quick. We had to write the main. and then explore and write some first tests. And that's normal. Writing the first test is always the hardest part. And then you'll find once you've got the first test, it becomes easier and easier to add a second and third and so on. So what that means is if you're writing your first ever test in a particular environment or framework, it's really important that you make the first test as easy as possible, because it is going to be hard anyway. And then if it was hard, write a few more tests before deciding whether it's a good idea to carry on. So I'm going to pause again and see if there's any questions, and there aren't, so I will move on again. So this is my second Super Collider example, and we're moving on to something a bit more complicated now. And in the Super Collider IDE, you see some Super Collider language code, and then at the bottom there's what it calls a go-to-line panel. And you can type a number into the box there, or click on the up-down arrows in the spinner. I think in practice people would always type a number in, and then click on the go button, and your cursor should move to a different location. And so the go-to-line panel was another small chunk of code that I could look at to start experimenting with. So I'm going to demo some basic code to test this. I'm going to show you 3 different versions. And especially in the first version, there's a lot of detail because I want to show you the sort of thing is needed. And then later on, I'll show you how to avoid it. But in each case, I'll go through the arrange, act, and assert steps. And you'll see in the first version what a huge amount of arrange code is required to get testing. So we start with our first arrange slide. And what we're testing is that the go-to-line tool emits a particular signal when the go button is clicked. And we start by creating a go-to-line tool widget, and then we have to call raise and show to make the widget visible. And then for this test, we're going to say, pretend we're editing a document which has got 27 lines in it. Now, in the main application, the document model, something like that would take care of this, but we don't want to set up all of that associated code. We do whatever we need to be able to test this widget in isolation. Some of these things, the raise and the show, the Qt test framework takes care of, but because we're driving this with Catch, which is a rather more expressive test framework, the trade-off is we have to do some more homework ourselves. And then we set the focus so that any actions we trigger definitely go to this widget rather than whatever else is visible on the screen at the time. And so in our tests, we want to do things to the spin box, and then we want to click on the go button. And those widgets are private in the source code. And in this first test, I'm going to not change the library that we're testing, and that means we need another way to get hold of these widgets to test. And Qt widgets have find child to say within this dialog or custom widget or whatever, find me the first object of this type. So we're saying get a spin box, find the first spin box in our go-to-line tool widget. And then because this is a fragile thing to do, because the code may change in future and no longer have a spin box, we require that the value we get back is not null. Catch will halt this test whenever require fails. So yeah, huge klaxons should be going off. Find child it's a fragile thing to do. You're peeking inside the implementation of a class. Especially don't do it in production code, but it's what we have available to us for now. And it's more important to write a test than worry about the code being perfect. So what we're going to test is we're going to simulate the user typing a 1 and then a 7 into the spinner text box and then clicking on go. And then what should happen is that custom widget should emit the signal activated and say that it's requesting a change for anyone else who's listening, and the value is 17. There isn't time to go into Qt signals and slots in any details, but a very simple explanation you can think of. I have got those completely the wrong way around. A Qt signal is the special method for announcing changes, and a Qt slot is a special method for responding to changes. And you connect those together. And that's a really important part of how Qt allows separability and reusability of code. So in the IDE, what would happen when the signal was emitted is that the cursor would jump to line 17. In our test, we don't want to have to set up all of that code. So instead, we're going to use a Qt testing capability called QSignal Spy to listen out for signals. So we have more arranging code. We're creating a QSignal Spy. We're calling it activated spy because that's the signal that it's listening out for. We're passing in the widget and the pointer to the member function. That is the signal that we want to listen out for. If you're using, and we have to, it's strongly documented that you should, after creating a spy, you should check that it's valid so that you don't get tests silently passing through the code not being set up correctly in the test. If you're using Qt 4, you might be familiar with the old style macro-based connections, and that's what that would look like. So we've now got onto the act stage. So Qt Test has some helpful functions for generating events during testing. So the user is going to click 1 in the spinner, and then 7, or our simulated user, and then click on the Go button. And finally, we get to our assert. So we're going to require that the activated signal was emitted once and once only. So a common cause of errors is in Qt code is signals being not emitted or emitted too many times. So we're checking it's only emitted once. So this would be a valuable test to keep. And then we want to test that the value in the signal was 17. I'm not going to go through that boilerplate code. In practice, you would hide it behind a helper function. So as a quick reminder of version 1, the class that we're testing is GoToLine It's got private widgets inside, and we're writing a catch2 test case that has to peek inside called findChild to test those widgets. This is painful. You want your tests to be super easy to write. You don't want tests to be hard to write, and it's important that it's obvious to anyone reading them what's going on. And findChild is fragile. It's prone to future breakage, and if you get it wrong, you don't get a compile time failure. A small improvement, though, is to use findChild and supply it an interface type rather than a concrete button type. So if I'd searched for Q abstract button, then in future, if somebody changed from using Q tool button to one of the other button classes in Qt, Q abstract button would still find the widget we wanted. So you can make the code a bit safer, but try not to use findChild. So what could we do? So the first row in this table represents what you've just seen, and the next row is an alternative. We could add a public accessor to our GoToLine class for each of the widgets that we want to test. And that's a bit smelly. It's exposing internals within the code, and it perhaps encourages misuse by other developers. But yeah, it's a possibility. So here we have added public methods to GoToLine to access the widgets we need for testing. You could chain call the functions spinbox only used for testing, and that might make it a bit less likely it would get reused. And now our test code is a bit cleaner. But it would be really nice if we could hide the implementation details in even better and make our tests more general, more readable, and try to guard against changes in the implementation of the code that we're testing. And for this, I'm introducing an intermediate class, commonly known as a fixture. So I've called it go to line tool fixture, maybe test fixture if I got more space might be a better name. And it contains a private instance of the thing that we're testing. And then it has public methods that are expressed in the vocabulary that expresses what we're trying to do in testing. So we're simulating typing a character or clicking a button, that kind of thing. So only the test fixture knows about the details of the class being tested. And then you can have lots and lots of different tests written using that fixture. And in catch, you say test case method and give a class name to use that class as the test fixture. And then you write your tests in terms of that expressive vocabulary, the expressive methods you've provided in the test fixture. And that's really lovely. So inside the fixture, we can hide away a lot of the details. So we've got a private widget that we're testing. Managing the lifetime of the spy is a little bit harder because it can't be created until the widget has been created, but that's all hidden away. And then you can also hide away some of the annoyances like raise and show and things. Take care of those inside the fixture. Those are private. That's really important to hide the details. When I first wrote this, they were public to start with, and then I worked towards making them private so I could introduce the fixture gradually. Catch uses inheritance with fixtures. So when you write test case method and give it a fixture name, that generates a class. So test case method generates some long class name you never need to worry that inherits from the fixture code. So all the public and protected methods in the fixture, you just call within your test code. And so this is what that test code, the many screenfuls, the many slides that I showed you previously, this is version 3. This is what we've ended up with. So we're using a fixture. We've given it a sensible name. The test go to line tool emits signal when the go button is clicked. We only have to set the maximum line count, type a character 1, type a character 7, click the go button, check that the signal was emitted once and that it contained the value 17. And I think that shows how it's possible to write expressive, maintainable tests. And maybe you want to add another test which says what happens if somebody types a number that's larger than the maximum line count. You can start to explore the behavior. So that's the sort of thing that I try to aspire to when writing tests, and fixtures make that really easy. I'm going to gloss over the detail of how the fixture, because the fixture still needs to access the widgets inside the class that we're testing. We could keep the public accessor, we could make a protected accessor and use inheritance where the fixture inherits the thing that we're testing, or we could add private accessors or even access the private data and make the test fixture a friend of the class that you're testing. None of those is perfect. You have to hold your nose and decide which approach you think is best. I like the last one because it gives better encapsulation, but it's a personal decision. Bonus points on this, I showed you originally how we'd separate our GUI executable out into a library and some separate tests. Better still would be to separate out the data storage and logic, business logic, algorithms, that sort of thing from the UI library. So behind this is often when people first write GUI code, they tend to mix in the code that implements the requested changes from the user interface with the GUI code. And so what we're saying here is separate out domain model type code into a lower level library and have your UI library depend on the model code, but not the other way around. And then, of course, you can write separate, simpler tests that test your model. And you would expect to have many more tests of the model than tests of the user interface. So over time, you get to separate the code and make it more maintainable. And that pays benefits in terms of productivity, robustness, and so on. So I'm now going to pause for questions, and we do have some. So question, is this testing methodology a valid alternative to something like Squish, or are they completely different? I have a slide on Squish at the end, so I'll defer that one till then, but it's a very good question. I know you said find child is fragile, but what happens if you have multiple children of the same type you need to test? Then there is a find children method that will return multiple values, and you would need to have a way to distinguish between them and know which one you wanted. So perhaps name the widgets. Can these same methods be used to test Qt QML applications? My experience is in working with desktop Qt applications, and I'm looking forward at some point to working with Qt and QML, but for now I don't have any experience on that style of Qt development, and that's why I've focused on desktop applications. So I am going to have to pass on that one. If anyone's watching and does have experience with this kind of testing of QML applications, I would love to talk, see what I can learn and share in future talks. So thank you for the questions. There's a few things I wanted to flag up as things which are error-prone and things to specifically look out for and test. So I touched on this previously. If you are using Qt 4 or you're working in Qt 5 on code that was written in Qt 4 earlier, your signal slot connections will look like this. They use a signal macro and then a slot macro. And the code behind the scenes is string-based and only checked at runtime. And if you get that wrong, for example, if there is no slot method called quit, then at runtime in the console, if you're lucky enough that your application has a console, someone will see error output like this. If you don't have a console, a user will complain that the button was broken. Much safer is to use the Qt 5 style pointer to member function, because if you get this wrong, you know at compile time. I mentioned briefly later a tool that will port code from Qt 4 to Qt 5 connections. Another thing to be aware of is event processing when you're writing tests. So you'll know that in a Qt application behind the scenes, Qt core application process events is trundling away listening for user events, timer events, things like that. And when you're writing your own tests, you can't rely on that. And there are some options available. I just wanted to flag them up so that you could search for the documentation and use them. So Qt Test, it's really worth reading up on the Qt Test library. It does make it a lot easier to write developer-driven automated tests. And QSignal Spy has weight as well. Obviously, it's not a great idea to put in hard-coded wait for 3 seconds until an action happens, however many seconds, because sooner or later your code is going to be running on perhaps a build virtual machine that is starved of CPU time for a while, and you'll get flickering, failing tests. So try really hard not to put hard-coded time values in any test that you write. If your test runner is Qt Test, so your main is created by Qt Test, then you can use these macros, qtry, compare, and friends. But beware if you have several assertions in one test, that if any of those fail, the Qt Test framework returns from your test case, and so your later assertions won't be executed. Big klaxon. If you've written your own test main in catch or whatever, don't use any of these methods unless your test framework, your test is being run by the Qt Test framework itself. I'll explain a bit more later on why. Once you've written your tests, any tests that you write, you want them to be run automatically in a build system, in a continuous integration system, because they pay for themselves over their lifetime when future developers make a change that they don't understand has broken some prior commitment. On Windows, you'll find that Qt GUI tests just work in a CI system. On Linux, you need to set up a virtual display. Typically, the CI machines don't have monitors attached. XVFB is one that is commonly used and easily searchable for. Both for developers and CI builds, it's worth being aware of Qt's command line argument -platform off screen. So a developer running tests doesn't have to have all of the widgets flickering up and disappearing, can use an off-screen display. As far as I know, on Mac, you need to keep a user logged in order for GUI tests to run. If you find you've got a test executable that's got some tests that require a display environment and some that don't, then a nice trick is to create a macro or some one-liner that says, if there's no GUI, print a message saying I'm skipping this test and return. Put that at the top of each test that depends on a GUI, and then all of your other tests can run gracefully when no display is found. There's a question about dealing with flaky tests and how do you deal with those. I'll answer that at the end if there's time, or let's talk about it in Remo afterwards. It's not a short answer, and I want to try and focus my answers on things that I'm covering in the talk. Don't worry, don't hold off. Please keep asking them, but I'll for now pick out the ones that relate to stuff I've covered so far. So everything I've shown you so far is vanilla catch 2 and Qt testing. Now I'm going to go on and talk about approval tests. And I'm introducing a tiny, tiny testing library, which is built on top of approval tests for C++, approval tests for testing Qt. And then the naming convention might seem curious to you, but it fits with the many other repositories in the approvals GitHub user. So this is a library that so far is built upon approval tests for C++ and catch 2. I expect that if there's any demand, I'll add support for more test frameworks in future. You need to provide your own build of Qt 5 test and Qt 5 widgets. And the goals that I have for that library are to enable you to rapidly start testing Qt code. So what are the boilerplate main that I showed you earlier? I provide a way to use that without having to replicate it yourself. So that little bit will be useful even if you don't use the approval tests functionality. And then to start making it easy to add approval test support for a few Qt types. So easy saving of the state of widgets in golden output files. I'll demo that shortly. So we're at a tentatively very, very early version to represent the early state that the code is in. And one of the big purposes of this talk is for me to explore whether there's any interest in doing more work on the library. It really is very prototype early version. We do have a starter project though that you can download and build an NECmake supporting IDE. So your main, if you use this library, you could write hash define approvals _ catch _ Qt, and then hash include the approval tests Qt header. And that is the equivalent of all of this code that we wrote by hand earlier. So that's the kind of help it can give you in getting started. Now imagine that you are trying to write a test for some table widget. And I talked earlier about implementation code being mixed into widget code. Imagine that the code to populate this table was mixed into the code that calculated the values was mixed in with the code that displayed the values. And you wanted to reuse the calculation code somewhere else, so you wanted to separate it. And so because of that, we want to test the text values in the table cells. And let's look at how we would do that. So I've got catch header and the approval tests header, and I've got some function that for the purposes of testing creates populates the cells in a table widget. So here we have created the table widget. We're calling our populate table function. And then we're going to call approval tests Qt verify Q table view. Now, people who've seen approval tests before will recognize this pattern of having a verify method and passing something in, and then the state of that object being preserved as a kind of regression test, a very convenient regression test, so that once you've told approval test what the right answer is, in future runs, it will report if there are any changes. So let's try that out. Let's run it. And it said test failed. And the error message was that the approved test was not found. And so on the left-hand side, we have the output from this test run. And on the right-hand side, we have the right answer. And of course, approvals doesn't know the right answer because this is the first time we've run this test. And as is often the case with legacy code, what it writes out for the time being is the right answer. So I clicked on the little arrow to copy the output, the received output, to the approved file. And I'm going to save and quit that. And now when I look in the tests, you'll see in the approval test subdirectory, we've got an approved file that's populated. And we would check into version control that file alongside the test source code. That is the right answer. That's the expected output. And when I rerun the test, approval test only shows a differencing tool if there's a change or a test failure to show you. So now it's a silently passing test, which is great. The other capability that this new library has is the ability to capture screenshots as images. And in general, I want to reassure you that I do understand that this is not a good way to write tests of GUI code. You want to focus on testing behavior, not appearance. Those tests are fragile. They can be changes, they can start failing when there's a minor update to an operating system. They'll behave differently, give slightly different pictures on different platforms. So this is not the way to test that appearances are unchanged. You really want to test behavior. However, just occasionally, it may be valuable to test save screenshots. So let me switch to the other example here. Now, I'm going to have to ask you to use your imagination here. Imagine that behind the scenes is some beautiful code for creating some beautiful image. And we're calling create our example image, and then we're passing that into approval tests Qt verify image. So the test fails, and what appears is the actual answer. This is Araxis merge, which supports diffing of images, but it doesn't give us that much useful information. And so what I'm going to do is, there's multiple different ways to do this, but I'm going to tell approval tests to use the Beyond Compare reporter, because that does a much nicer job of comparing images. And so there's lots of extra information displayed, like the file modification time, the file size, the bit depth, all sorts of things like that. This shows a weakness of the library so far, which is that it doesn't know how to create empty PNG files. This probably isn't the best approach for testing, and I'll include a link in the notes from the talk, but somebody has written an approval tests for images library that is much more sophisticated at working with images. So I very much recommend using that, but this capability is here. So I did use this sort of approach when I was working on some crystal structure visualization software. This is the sort of thing that the code was generating. And as I was adding a new capability, and I was implementing iteratively, finding lots of corner cases. And in my talk at C++ on C in 2019, I talked through in more detail how I was able to use approval tests with Qt code. And it was really, really helpful. Sped up development significantly. Quick note of caution, a bit more about the avoid Q compare and so on. If your test framework is anything other than Qt Tests, any failures in those will be silently swallowed and your tests will spuriously pass. That's why you need to avoid it. What's next for this library? I do want to fix Qt Test macros problem, and Fabian from Qt has given me some really helpful information on that. Then I think I'd like feedback. There's lots of things I could do, but first of all, I need to know if there's actually anyone interested in working on it and testing it out. So yeah, let me know if you use it, if you want to use it, what you think would be helpful. I'd be really happy to do more work. So let's look and see what questions we've got. Okay, so no new questions, so I will continue. Just briefly, 3 tools that I wanted to mention. KDAB's Gamma Ray is a fantastic inspection tool to allow you to navigate through the widget hierarchy in a running Qt application. So if you were being asked to work on a particular area of an application and you wanted to find out where that source code was, I worked on a 4 to 5 million lines of code base, and when you worked in a new area, it was quite hard to find the code of interest. This would have really helped with that. Clazy is a static analysis tool that speaks Qt or Qt. It's got lots of useful warnings to point out errors, likely errors, and inefficiency problems in code, Qt code, and it has a fix-it for old style connect. So that's how you can, if you want ports, update your Qt 4 style connections to Qt 5. And then finally, Squish, which somebody asked about earlier. So everything else so far, up until this point, has been about developers editing source code and writing tests. Squish is different. Squish runs your whole application, and it's kind of semi-opaque box testing. So you record actions in your application. You've picked a language that your tests, the recordings will be saved in. Python was the one that I used. And then you refactor your code into reusable tests. There was a lovely talk at Qt Desktop conference in the last week or 2 showing actually how to use Squish and like BDD style tests. And it kind of does the refactoring for you automatically. So when the video of that is published, I'll add it to the notes from this talk. In my opinion, it's not a replacement for unit tests. By virtue of it running your entire application for each test that it runs, it's going to be much slower if it's a sizable application. And it does require commitment to training and maintenance. But if you can use it well, and if you can make sure that you're running its tests automatically regularly so that any test failures are picked up quickly, it can replace huge amounts of manual testing before releases. So I think it's a really powerful tool. So in summary, it's never too late to start testing. I would like that to be the main message of my talk. Don't be put off if you've got no tests. It's never too late. Once you've written the first test, it will get easier. And it's a skill to learn, but it will pay for itself very quickly. Try to test smaller units of code, such as individual widgets. So write your tests in layers. Test behaviors, not appearance, as much as possible. And keep your application logic separate from the GUI code. Make tests easy to write, if that means writing helper functions, whatever it takes, and hide the details of the custom widgets behind, as I said, behind helper functions. Fixtures can enable you to write really expressive and readable tests. And I don't think this just applies to GUI code. I wish I'd understood the benefits of fixtures early on in my development testing career. And finally, any feedback on approval tests for Qt would be really welcome. And that is how you quickly test Qt desktop applications with approval tests. Thank you very much. Okay, so a little bit more information. A reminder that you can get via this bit.ly link or that QR code to a page of links that I've mentioned and some extra information, like tips on refactoring and things like that. As I get asked questions, I will, if anything else crops up, I'll extend that file. As I said, my focus is all about sustainable and efficient testing and refactoring of legacy code. I really hope that what I've told you will enable you to get started with testing on your own. But if you do need help, feel free to reach out. Really happy to answer questions, and for more substantial work, I can work with you remotely for half a day, a few days, whatever it helps to get you unblocked and start testing. That's how to contact me. And that's it. So there are a few minutes left. So the one extra question is, do I have any suggestions on how to get Catch 2 to compile faster? So particularly for its main, Catch 2 has a lot of code to compile. And when you're using Catch 2 version 2, they have a helpful page of some extra options that you can set to speed up builds. I'm assuming that you would have a main file and then your tests in separate files. Definitely don't put tests in the same place as the main. If you can, I would recommend seeing if you can build against Catch 2 version 3, which is on a branch, but I know that people are already using it on production code. And it's moved away from the single header approach to having a static library. So that code gets built once, and then when your code is compiled, the compiler only needs to see the header and not the implementations. And that will speed up your builds a lot. A leftover question. Have you dealt with flaky tests? How did you deal with those? Thank you for the reminder, Kevin. So yes, flaky tests are a real problem because they mean that people stop trusting the tests, and it also means they stop dealing with test failures, which is a real disadvantage. So the kind of thing I've seen is a particular library, the test for a particular library started failing a week ago, and for whatever reason, they hadn't been fixed in between. And then sometime later, a new test starts failing in the same library, and people don't pay any attention. The CI system says that library is red, the build is red, the test failed, and someone says, oh, don't worry, it's been like that for a while. We'll prod so-and-so to look at it when they get back from holiday. So the number one thing is don't tolerate flaky tests. I've dealt with flaky tests that turned out to be perhaps a circumstance of timing. I mentioned earlier that don't ever write a test that says, for example, test this function is at least 3 times as fast as this other function. Don't write things that depend on timing, because sooner or later your test will run on a CI system that's starved of resources. So that's my number one thing, is just don't write tests that depend on timing. If you need to do performance tests, have a separate environment for that with stable hardware that gives stable performance. I tended to find, the other thing is don't ever ignore a flaky test. In most flaky tests that I've seen, when we finally investigated them, they've been telling us real things. So if you're writing tests in Qt code, testing how an application manages its settings, Qt settings object, those by default are saved in the home directory. And if your CI system runs in several different tests simultaneously on the same user on the same machine, you might get flickering tests where two applications are trying to change the setting. Two different sets of code are trying to save to the same settings file at the same time. And that will only fail occasionally. And you can change Q settings to tell it to give it a location to store the file. So that was a real flickering test that we were able to improve our tests for. Most of the time, so you'll find there are patterns, and it's worth documenting those and sharing them with colleagues. So usually, in my experience, a flickering test is telling us something real, something we need to look at. If you can't fix the flickering test at that point, then I would say disable it. Well, if it has no value, delete it. If you think you need to come back to it, then disable it with a comment that says disabled, or better, make it write out a message. So use your test framework's way of disabling it and say, disabled until we can fix GitHub issue 12345. Log an issue for it and make sure it gets prioritized. Don't just leave it in there, and definitely don't just leave it in there flickering occasionally. So it will devalue the rest of your tests. So I said it wasn't a short answer, but I hope that was a useful answer. So we have got about 4 minutes left, but there don't seem to be any more questions. So thank you very much. I think I will leave it there. ClareMacrae.co.uk if you would like to get back in touch with me. And otherwise, see you in Remo shortly. Thanks ever so much, and goodbye for now.